Okay, now it's the second of today's class, and sometimes this equation is called the Cauchy's theory, and the elements in the first row represent the stress components for the positive x surface. Also, if we consider the negative x surface, all the stress will be added to a minus sign. And the second row represents the stress components for the positive y surface or the negative y surface. However, if you are considering the negative y surface, you need to add a negative sign to all the elements. And the third row represents the stress components on the positive z surface or the negative z surface. And that's the unit vector for the normal, usually we call it is the normal vector, or it is the unit normal vector. And if we multiply this matrix to the normal vector, you can say actually we are trying to project the surface traction for the negative y, negative x, and the negative z surface to the normal direction of this one. Then we can get the so-called the surface traction for the inclined surface. Just like the first row represents the surface traction for the x surface. The second row represents the surface traction for the y surface. Okay. Then if we try to solve the principal stress or the principal directions, after we solve the principal stress, the normal vector is just the eigenvector. The eigenvalue represents the principal stress. The eigenvector represents the principal direction. So if we know the stress state of a certain point inside the structure, so usually we represent the stress state by usually we take the orthogonal directions for the x, y, z. So that's why we usually use these 9 components to represent the stress state of a point. Why we say for these 9 stress values, it can represent all the stress conditions for this point. Since we can use the Cauchy's theory to calculate any inclined surface to get the surface traction for this inclined surface. Okay, so we can. It is also possible in structure analysis problems that we need to solve the eigenvalue and eigenvector problems, even it is a very small dimensions. For these small dimensions problems, you can use the computer to help you to solve the problems, or you can use the hand calculations to solve the problems. But the numerical methods usually emphasize on the applications of the computer programs. So most of the time we are not so interested in the hand calculation methods. However, in these problems, you can also learn how to solve the solutions. would like to use this opportunity to introduce you if we like to solve the roots or the of the equation. If we like to solve the roots of the equations. Okay, so for a problem like this one, we have three solutions. Okay, so for these 3 points, they are the f of x equal to 0. So we can solve the x1, x2, and x3. Okay, so at these 3 points, it can fulfill the f of x equal to 0. So we will say the x1, x2, and the x3, they are the 3 roots of the f of x equal to 0. They are the roots of these equations. And how can we solve the roots of this one? The first method is called the bisection method. The first method is called the bisection method. And for the bisection method, if we know the approximate range, in this range we can have, if we can locate a solution in a small range. For example, if we know this one is the, let's say that's the x0, and for this one, point is the x1.5. Okay, what are the typical points for these 2 points? If we know if we multiply the function values of f of x0 and the f of x1.5, so if we multiply the function values of these 2 points, it must be less than 0. So it means the f of x0 and the f of x1.5, they have different sign conventions. In this example, the f of x0 is a positive value. The f of x1.5 is a negative value. So therefore, if we multiply these 2 functions, these 2 points functions, if we multiply these 2 values together, it is a negative value. It is a negative value. Okay, we don't need to find very close, or as long as we can find the 2 points near one, near one of the roots, but they have different sign. And usually it is required the f of x must be a continuous function. So you cannot have the functions, if you draw the function lines, you cannot have the discontinuous conditions between these 2 points. So as long as the f of x is a continuous function, and also we know at these 2 points we have different signs for these 2 points. The function value of at these 2 points, they have different signs. Okay, so we know the between so we know between these 2 points, we have one solution. Between these 2 points, we must have one solution. Okay, then what do we need to do for the bisection method? then the next thing, the first step, okay. So we need to find the 2 points x0 and the x1.5. At these 2 points, the f of x should be with different sign. Then we need to find the okay. Then we need to find the center, the middle point. Let's say that's the x center. Okay, so we can solve the center point between these two endpoints, and then we can solve. Then we can solve the xc, the f of xc, and okay. So the next step, we need to find the endpoints, which got the same sign conventions for the f of xc. Okay. So in the previous examples, we know the f of x0 is positive value. F of x1.5 is a negative value. So if the f of xc is a positive value, then we need to replace the x0 by the xc. But if the f of xc is a negative value, then we will replace the x1.5 by the xc. Okay, so then we will go to the next iteration. Then go to the next iteration. So the next iteration is, again, we have the x0 and x1.5. Okay. Between this range, the x there is one solution in this range. So between the x0 and the x1.5, we got a root between these 2 points. But if you check the interval of this iteration, it is only 1/2 of the first iteration. Since the one of the endpoints, actually it is the center point for the previous example. So range okay. The range of the considered range will be one half raised to n times the original range. Okay, so the range will become smaller and smaller. After several iterations, the range is smaller enough. If we consider the precision requirement for the problems, if the range, after several iterations, the range will become smaller and smaller. If the range is small enough, then the center point okay. So if the range is small enough, then we can take the center point, the final center point, as an approximate solution, for the root. Okay. So if we use the bisection method, we can find all the roots of this one. Okay. If both A and B matrix, they are the symmetric matrix, then we can we know the solutions of the if we check the characteristic equation, you will find all the eigenvalues. They must be the real solution. They must be the real solutions. And if the A matrix and the B matrix, they are the n by n matrix, n by 1. Okay, so we could have n different. We could have n different real roots, or we could have less than n. The number of the roots could be equal to the number of the n, or they could be less than the n. Okay, but we can guarantee that there is no. We do not have the imaginary line solutions for the eigenvalues. Okay, so for example, if the n equal to 3, so that's the 3 real roots. Or we could have one single root and one double root. We could have one single root or one double root. That's the double root. is the single root. Or another possibility is this is the triple root. Okay, so we could have these three conditions. The first thing, the first possibility is we got three different real roots, and the second possibility we have two real roots, but one is the double root, the other one is the single root. The third possibility is we got only one real solution, but the real solution is a triple root. Okay, so if you like to use the bisection method to solve the problems, the first thing you could draw roughly since the characteristic equations is